Welcome to Study Loop.
In this problem, instead of a rock, we have a bucket hanging from this pulley. So now this is a bucket, not a rock. But we have the exact same situation going on. And now the bucket, let's see here, no, the bucket weighs 15 kilograms. So this is, I should actually call this W2 and this is W1. So this weighs 15 or it has a mass of 15 kilograms, and this has a mass of 12 kilograms and a radius of 0.3 or 30 centimeters, 0.3 meters. And let's see here, why the bucket is released from rest at the top and falls 10 meters to the water. So it's kind of in a well. And we want to know what is the tension of the rope while the bucket is falling, and with what speed does the bucket strike the water, and what is the time that it takes to fall. And while the bucket is falling, what is the force exerted by the cylinder by the axle, on the cylinder by the axle. Okay, got lots of stuff here. So let's see. Free body diagram of our bucket. We get positives down, we get W minus T equals M2A. Again, since we're assuming that there's no slipping here, the acceleration of the bucket is the tangential acceleration of the pulley, so that's A equals R times alpha, the angular acceleration. We get T equals M2, so plugging in for the weight is M2G, so T equals M2 times G minus A, or M2 times G minus R alpha. Summing moments about the center here, or the axis of rotation of the pulley, the torque is T times R, the tension in the string times R, and that is equal to the mass moment times the angular acceleration. The mass moment of a uniform pulley is 1/2 mr squared. We can then plug this into here, and again we do exactly the same as problem 12. We get M2 times G minus R alpha equals 1/2 M1 R alpha. Now, we find out, now in this case we know what M2 is. We're looking for alpha. I actually then substituted in A. This goes to A, this goes to A. And then we can solve for A. So because we wanted the acceleration, the linear acceleration instead of the angular, I substituted back in. And so now we get the acceleration of the bucket is M2G divided by 1/2 M1 plus M2. Now we can see if M1 is 0, so let's see if this pulley has 0 mass. That goes to 0, right? And then we get A equals G, because then this is just under free fall. So makes some sense. And so we could plug in and we get A equals 7.00 meters per second squared. And again, we can see that because this has mass right here, because this has mass, we're actually slowing things down. Now we can just go back up here and plug in A, what we found, G and M2, and get T, and that winds up being 42 newtons. So while this is falling, there's 42 newtons of tension in that rope. Now, let's see here, which is much less than the weight of the bucket. So now they ask what speed does this bucket hit the water after it goes 10 meters. So we know the final velocity squared equals the initial velocity squared plus 2 times the acceleration, which we're assuming is a constant, the constant acceleration times the distance over which it acted. Initial velocity was 0, so we get, solving for this, we get it's just the square root of 2ay. We know all of that stuff, and the final velocity then is 11.8 meters per second. Now, we also know that y, the distance, is 1/2 at squared. We can then find, we know everything in this equation except for t, so we can solve for t, and we get about 1.7 seconds. So it takes about 1.7 seconds to hit the water. And then they want to know what the reaction force is at on the pulley here. And the reaction force in the x is 0 because there's no other force acting in the x direction, and the acceleration is 0. So the reaction force in the y, there's no acceleration of the center of mass of this pulley in the y direction, so we just have Ry minus W minus T equals 0. So Ry equals W plus T, and that is 160 newtons.